Under the accelerated bridge construction method, 8 massive deck bulb T-beams were installed at the Manhan River Bridge in East Hampton, Massachusetts. Each beam measured 93 feet long and weighed approximately 100,000 pounds. A high-capacity crane was brought in to handle the lifting, carefully maneuvering each beam from custom transport trailers into place. Workers guided the beams using tension ropes, ensuring accurate alignment as they were lowered across the river. The first placement required extra time for precision adjustments, while subsequent installations became progressively smoother. Despite intermittent rain, the crew remained on schedule. By the end of the day, all 8 beams had been positioned, transforming the site from a river gap into a recognizable bridge structure. Normally a process that could span weeks, this phase was completed in just 8 hours, showcasing the efficiency of modern bridge engineering and teamwork on site. With the superstructure in place, the project now moves forward to decking and final assembly. Modern quarrying has been transformed by diamond wire technology. Instead of blasting or wedge splitting, operators now use motorized wire loops embedded with diamond beads to slice through stone with minimal waste. Front-end loaders handle multi-ton blocks, replacing outdated derricks. In the slabbing phase, machines equipped with up to 20 diamond wires reduce cutting time from days to hours, processing granite blocks at speeds of up to 14 inches per hour. With fewer workers, quarries like North Carolina Granite now produce more stone than ever before. Combined with computer-guided profiling systems, this tech makes high-volume stone production faster, safer, and far more precise. Step inside the modern stone industry, where Marfilpe transforms raw limestone and marble into refined slabs. Quarrying begins with diamond wire saws cutting blocks at sites in Portugal and Angola. These blocks are transported to the factory, where multi-wire saws slice them into uniform slabs. Automated polishing lines finish the surfaces with controlled texture and gloss. After quality checks, the slabs are packed for distribution. Each step, extraction, cutting, polishing, inspection, is streamlined for high efficiency and consistent results. Red-eye rock retaining walls are built using large precast concrete blocks. Crews start by leveling the base, then stack each block with heavy machinery. Interlocking grooves help secure the structure during placement, ensuring a stable and durable wall. WarmFloor Pro combines precast concrete beams with expanded polystyrene infill blocks to create an insulated ground floor system. Installers lay the beams across foundations, slot in the EPS blocks, then add a structural topping, forming a fast, energy-efficient flooring solution used widely in housing construction. In just one weekend, crews installed a new underbridge beneath the Cork-Dublin rail line. Prefabricated concrete sections, built months in advance beside the tracks, were transported into place after rail services paused on Good Friday at 0:30. Excavators removed the existing track and ballast, then lifted in each bridge segment using heavy cranes. Once aligned and secured, the track bed was rebuilt and rails reinstalled. By 10 o'clock Easter Monday, construction was complete, just 2 hours before train services resumed, minimizing disruption on this major national line. Pre-stressed concrete requires precise tensioning systems, and here each step is handled with specialized equipment. At the start of the casting bed, abutment anchor posts and transverse anchor plates are installed as permanent fixtures. Then, mobile stressing tools come into play, ranging from 30 to 300 kilonewtons single-wire jacks to twin ram jacks and screw jacks, powered by high-pressure pump units. Steel cutters and wire/strand pushers are used to handle reinforcement efficiently. Once curing is complete, detensioning pump units and cylinders, some rated up to 10,000 kilonewtons, gradually release the tension. Special detensioning anchors ensure safe load transfer. The system ensures structural strength, consistency, and speed in pre-stressed concrete production. In this video, we observe the construction of the Mangyang River Bridge, part of the Honam high-speed railway, using the precast span method, PSM. This advanced method involves the fabrication of 25-meter-long box girders in a controlled factory environment, ensuring high precision and quality. After production, these massive girders are carefully transported to the construction site using specialized equipment. The PSM method allows for quick and efficient installation, significantly reducing construction time. By utilizing specialized machinery for the lifting and placement of each girder, the process is streamlined, enhancing overall safety and quality. Factory-based production ensures uniformity in the structure, while minimizing errors associated with traditional construction methods. The PSM method has proven to be an excellent solution for building large-scale bridges with fewer resources, achieving faster project completion without compromising on safety or structural integrity. This technique offers impressive cost efficiency and is a reliable choice for modern infrastructure projects like high-speed rail systems. In this video, we see DN1500 microtunneling systems in action on the MRT Green Line North cable tunnel project in Bangkok. The DN1500 systems are designed for precision and efficiency, allowing for the installation of tunnels in urban environments with minimal disruption. Using advanced microtunneling technology, the system enables safe, cost-effective, and precise tunneling without the need for extensive surface excavation. These machines are equipped with state-of-the-art tools that ensure smooth, uninterrupted tunneling even in challenging ground conditions. The project involves the use of cutting-edge technology to install a crucial cable tunnel, improving the city's transportation infrastructure. This modern solution ensures a quick, reliable, and environmentally friendly approach to urban tunneling projects. From the depths of a quarry in Honam, Belgium, blue limestone is extracted through a precise multi-stage process. Extraction begins with stripping layers of clay and gravel, revealing benches of limestone cut by rail-mounted saws with diamond chains. Massive blocks, some weighing over 100 tons, are split using pneumatic drills and hydraulic spreaders, then squared off and sorted. At the sawmill, gang saws slice blocks into slabs at 30 centimeters per hour. These are sorted by thickness and undergo various finishes: honed, flamed, bush-hammered, or cleaved, depending on the design needs. CNC machines ensure accuracy, while a trommel imparts a naturally aged appearance. Throughout, a closed water circuit system recycles quarry water. Traceability systems manage storage, while expert artisans oversee final shaping. This process turns ancient stone into refined architectural elements. Witness the construction of Ho Bin 1 offshore wind farm in Vietnam, where 13 turbines are installed using a 10,000-ton barge, showcasing efficient renewable energy development at sea. To build the Machu Bay Bridge, a 1,000-ton girder machine lifts and positions precast segments, each 40 meters long, onto piers, streamlining high-speed rail construction over open sea. The construction of the Barnstable Bridge was a significant project that began with the demolition of the old structure. The bridge's deteriorating condition led to the urgent need for a new one. The design for the new bridge was a 3-span pre-stressed concrete structure, with spans measuring 38 meters, 51 meters, and 38 meters, totaling 127 meters. The new bridge was built next to the old one, allowing traffic to continue uninterrupted. To improve safety, the ramp connections were redesigned with better alignment. The foundation work included installing piles in the steep terrain on both sides of the river to ensure stability. Construction of the piers began with specialized techniques like sprayed concrete for foundation stabilization. Overcoming difficult soil conditions and the tight construction site, the team used cranes for efficient progress. To ensure the bridge could withstand heavy loads and dynamic forces, advanced engineering methods were employed in the design of the pre-stressed concrete beams. The use of high-performance materials also contributed to the structure's durability and longevity. The new Barnstable Bridge not only enhances traffic safety but also meets modern engineering standards, providing reliable connectivity for years to come. The construction of the Casanuma Bay Bridge is captured in a time-lapse video that highlights key milestones in the project. The installation of the large main tower blocks began, progressing through various stages of the construction. More than 1 year later, the final closure of the main girder was completed. The video showcases the lower section erection and the installation of FC components, J3334, revealing the complex yet efficient process behind this massive structure. Each segment of the video reflects the dedication and expertise involved in building a bridge that will enhance connectivity in the region for years to come. The Puente de Vidalta project, completed in Mexico, showcases the complex process of bridge construction. From initial groundwork to the precise assembly of structural components, the video captures the critical steps involved in building this vital infrastructure. Discover the step-by-step process of asphalt production at a plant. The process begins with the collection of raw materials, including aggregate, sand, and bitumen. These materials are then mixed in a drum where heat is applied to dry and blend them. The final product is a high-quality hot mix asphalt which is cooled, stored, and transported for road construction. The Thames Tideway tunnel project, with a length of 25 kilometers, aims to intercept untreated sewage discharges, significantly improving the water quality of the River Thames. The project includes tunnel boring machines with a diameter of 7.2 meters, shafts, and extensive upgrades to London's sewer system. Witness the transformation of worn-out roads into smooth, durable surfaces. Old asphalt surfaces are milled away to prepare for a fresh layer of hot mix, ensuring long-lasting performance. The process begins with milling the damaged pavement, removing any deteriorated asphalt. Next, a high-quality hot mix is laid down, ensuring a smooth, durable surface. This method extends the life of the pavement while minimizing disruption. The project is a testament to advanced paving techniques, offering a cost-effective solution for restoring roadways. These lightweight blocks may look like Lego, but they're engineered for real homes. Made from expanded polystyrene, each hollow form is stacked to shape walls quickly and precisely. Once assembled, the structure is filled with concrete, creating an energy-efficient shell that's strong, durable, and ideal for passive house construction. At Cleland, North Lanarkshire, the Bellside Bridge, Scotland's most frequently struck bridge, was removed and replaced in just 54 hours. Prefabricated nearby, the 260-ton steel structure was moved into place using a self-propelled modular transporter that could rotate the bridge 360 degrees. During a full road and rail closure, crews dismantled abutments, installed the new deck, and rebuilt the track. The clearance was raised to over 5.2 meters, eliminating its low bridge status and improving safety for trains and road traffic alike. Bright white, solid, and surprisingly lightweight Yutong aerated concrete blocks are designed for efficient thermal insulation. This video shows the full process of building a non-load-bearing interior wall using Yutong blocks and thin bed mortar. The first step is preparing the surface and mixing mortar according to specifications. A glide foil is rolled out on the floor to prevent cracking due to ceiling movement. The first row is set in standard mortar for leveling. A spirit level and rubber mallet ensure alignment. Subsequent layers use thin bed mortar applied just 1 to 2 millimeters thick. Corner cuts are made with a precision saw, and any uneven spots are sanded. Masonry connectors provide secure anchoring to adjoining walls. Lintels made from the same material are easy to install alone and should be mortared at joints and bearings. To finish, any gaps are patched and elastic foam is used for the top joint, ensuring a quick, clean, and professional wall build. At Rupert Nuclear Power Plant, Royne World constructed multi-story concrete facilities near Reactor 1, using 3 tower cranes, 12-ton payload, heights 32 to 53 meters. 2 batching plants produce up to 100 cubic meters of concrete, supported by 10 mixer trucks, 7 m-cubed each. The project includes 5 kilometers of trestle overpasses, requiring 12,000 tons of steel, and 65,000 square meters sludge dumps, using 160,000 cubic meters sand, and 20,000 cubic meters concrete. Mid-American Energy's wind turbine installation follows a detailed and efficient process. Construction starts with excavating a foundation 10 feet deep and 100 feet wide, completed in 1 day. Up to 96,000 pounds of reinforcing steel are set within a day, forming the rebar cage. The foundation requires up to 53 concrete trucks to pour, and the concrete cures over 2 days. Afterward, 1,500 cubic yards of soil are backfilled and leveled. The tower assembly begins with the base section, 53 feet 11 inches tall and weighing 97,459 pounds, secured with 160 bolts. The mid-tower section weighs 115,587 pounds. The nacelle, about the size of a school bus, contains the generator, gearbox, and rotor shaft, and takes approximately 4 hours to prep and lift onto the tower. The rotor, consisting of 3 blades connected to the hub, is pre-assembled on the ground and then hoisted and attached, completing the build. The TESME 1475 cuts deep trenches for pipelines using a powerful rotating bucket wheel. As it advances, an integrated conveyor ejects soil and rock to the side, allowing for efficient, continuous excavation across varied terrains. Knives are crafted in Solingen, Germany, through 45 to 80 meticulous steps, with most tasks performed by hand. Production begins with high-quality steels like X50 CRMOV15, VG10 Damascus, or X65 CR13, selected for durability and sharpness. Blades are drop-forged or stamped, then hardened, using ice or vacuum methods to achieve 58 ± 1 HRC hardness. Grinding and polishing refine the blade to resist sticking and corrosion. Handles, often made from Andalusian olive wood, are manually assembled and polished for comfort and durability. Each knife is hand-sharpened by expert craftsmen, maintaining precise angles for optimal cutting performance. Final inspection ensures flawless quality before packaging. This process blends traditional craftsmanship with modern precision to create tools known for exceptional edge retention and durability, maintaining a reputation as some of the world's most respected kitchen knives since 1790. The Indeco ISS 45 hydraulic shear, weighing 9,700 kilograms, was used in demolishing New York's Kosciuszko Bridge. It provided 2,500 metric tons of clamping force, the 275-ton tip force, and a 1,100 mm jaw opening, operating at 5,100 psi. Mounted on a Komatsu PC800 excavator, it dismantled 31,500 metric tons of steel and 68,000 cubic meters of concrete, ensuring efficient and precise demolition with its dual guide and regeneration systems. In a groundbreaking trenchless engineering project, Malaysia completed its longest horizontal directional drilling (HDD) crossing to replace a damaged submarine water main supplying Pulau Ketum. Stretching nearly 2 kilometers beneath the shipping channel between Pulau Indah and Pulau Klang, the new 406 mm steel pipeline lies 16 meters under the seabed, installed with zero disruption to marine traffic. The process began with a 200-meter wash pipe installation, followed by pilot hole drilling using steerable downhole assemblies and precision tracking. Reaming enlarged the borehole from 311 mm to 762 mm in 3 phases. Finally, welded and hydro-tested pipes were pulled through the borehole using a swivel to avoid torque stress. Each pipe joint was inspected with cameras and underwent non-destructive and holiday testing to ensure integrity. This HDD operation significantly minimized soil excavation, 894 m³ versus 785,000 cubic meters with traditional dredging, making it a more sustainable and cost-effective approach. The result is a reliable water main with deeper coverage and enhanced environmental protection. The new Suez Canal project added 72 kilometers of channels, dredged to 24 meters depth and 317 meters wide. Completed in 12 months, 45 dredgers removed 250 million cubic meters of material, doubling daily ship capacity from 49 to 97. Towering over the site at nearly 200 feet, the SK3500D is one of the world's largest demolition machines. It's designed to safely bring down high-rise buildings, piece by piece. A telescopic boom extends upward, equipped with a massive hydraulic crusher. Operators dismantle upper floors from a secure distance, crushing concrete and steel with precision. Debris falls directly into controlled zones below, where it's sorted and removed. Its modular structure allows for transport in sections, then reassembled on site. Instead of explosive demolition, this method reduces dust, noise, and risk in urban areas. The SK3500D shows how modern deconstruction favors control over brute force. Spain's Duero Basin Authority initiated the removal of the Lotera Dam on the Bernesga River to power a small hydroelectric plant. The dam, located in the Alto Bernesga Biosphere Reserve, had long ceased operation and formed a physical barrier to aquatic life. Its presence also disrupted the natural transport of sediment and seasonal migration of fish species, hindering overall river health. The project began with careful site preparation. Access ramps were constructed using sediment and concrete debris from nearby restoration efforts, minimizing environmental impact. Native vegetation along the riverbank was preserved to stabilize materials during construction. Mechanical components were stripped from the dam's gate area before demolition began. Fish in the affected pool were relocated upstream using electrofishing. A controlled lowering of the water level allowed sediment, accumulated over 90 years, to gradually resurface and move downstream, reducing risk to aquatic habitats. Demolition crews dismantled the structure in phases. Unreinforced concrete blocks were removed methodically to prevent debris from contaminating the river. As the wall was broken down, water flow increased, helping redistribute sediment naturally. This removal aligned with Spain's national river restoration strategy and European water directives, promoting ecological recovery by eliminating obsolete infrastructure and restoring river continuity.